if you found this room, congratulations, because it's kind of like playing Pokemon Go. You don't know where it is. Right, well, there's an interesting fact about humans. Many of us were wired to be skeptics. It really doesn't matter what the topic is, whether it's politics or climate change, like somebody that I know back in the US. Many of us are just frankly natural skeptics. Now here's what people said about computers half a century ago. I think that there will be a world market for maybe 5 computers. Thomson Watson, chairman and CEO of IBM, 1943. Computers in the future may weigh no more than 1.5 tons. Popular Mechanics, 1949. I have traveled the length and breadth of this country and talked with the best people. And I can assure you that data processing is a fad that won't even last the end of this year. The editor in charge of Prentice Hall, 1957. There is no reason anyone would want a computer in their home. Ken Olsen, chairman and president of Digital Equipment Corp, 1977. And it's easy to laugh at some of these comments, but the reality is during that time, they meant it, and so did many people. They believed in it. By the way, so where are the 1.5-ton computers? Fortunately, we've managed to get down to just 1 millimeter cube that can sit on the edge of a coin. The Michigan Micromotes, or MQ for short, is the smallest autonomous computer in the world. And the researchers at the University of Chicago, or University of Michigan, worked on MQ specifically for the Internet of Things, so that everyday objects, whether it's toasters or washing machines or even doorknobs, can in fact have intelligence. Now, despite the size, it has the ability to take pictures, take reading of temperatures, as well as to record pressures. It can even be injected to the body to measure things like ECG, as well as other measurements. Well, maybe there's a good reason to be skeptical, at least about quantum computing anyways, right? Well, just look at the D-Wave system that claims to be the world's first commercialized quantum computer. And by the way, do you see the similarity with D-Wave and the IBM 7 series mainframe back in the 1960s? Is the D-Wave system a real quantum computer? That's the question. I'm sure, yes, you can solve problems, but if the noise of disentangling the qubits isn't there, it's just frankly this very expensive classical computer, is it not? Well, to test this, Daniel Lidar, the quantum scientist at USC, ran about 1,000 different tests against this thing. And what he found out was that the curvature looked more like a U shape, which meant that it completely failed or it completely succeeded, which is different from the classical computers, because classical computers would have more of a normal distribution curve. But to say that we have reasonable evidence that this has a quantum behavior, I mean, is that really accurate? Well, they tested against an Intel machine, and it turns out that it's actually slower, much slower than the Intel machine. So clearly no evidence of quantum speedup. But the other problem is that the amount of time that D-Wave needed to solve increased roughly at the same rate as classical computers. If the D-Wave was really harnessing the quantum dynamics, you would expect the opposite. So why isn't it working like a productive quantum system? Perhaps it's coherence time. We don't know. Well, you're probably thinking what I'm thinking, that quantum computer is purely a theoretical framework from quantum physics. And we'll never see this in our lifetime, right? Well, to the dismay of skeptics, there are serious and tangible progress that's being made on quantum computing. Now, you see, until now, quantum computers had just a fraction of the processing power that they're capable of, theoretically. But recently, an international team of researchers led by Professor Winfried Hensinger, the head of ion quantum technology group at the University of Sussex, they've actually shown that they can overcome the technical problems that's prevented quantum computers being built on an arbitrarily large scale. In a recent publication of Sciences and Advances, researchers unveiled the blueprint for a microwave trapped ion quantum computer that would enable large-scale quantum computing. Now what it does is it actually takes a modular approach and makes it possible to build this scalable quantum computer architecture based on the long-wavelength radiation quantum gates. And the modules actually control all the operations, and it's a standalone set of units, and it's constructed using silicon microfabrication techniques. And it's very much within reach of today's technology. Now, this is not the quantum computer, but rather the blueprint that you're seeing on the screen. That represents a full-fledged quantum computer. Now, as some of you may know, the problem with existing quantum computers is that they require these lasers to focus precisely on that individual atom, right? And the larger the computer gets, the more lasers that are required that has the potential of things going wrong. Now keep in mind, there are many different approaches that's being tackled at this point, and you can read about it in some of the academia. But the ion traps approach that they're using is very much a realistic and one of the earliest proposals that's out there. Now let's come back to IoT. Why am I talking about quantum computing when nobody else at this conference or the world is really talking about it as it relates to the Internet of Things? Aside from the fact that I am a futurist. Well, because if you've gone to some of the sessions today, what did you hear? What are the challenges or the obstacles that's hampering Internet of Things from being adopted on a wide scale? Well, let's take a look. According to the World Economic Forum, and it's a little bit hard to see here, it's obstacles such as security. We know that. It's one of the most important obstacles and issues facing IoT. Integration with legacy infrastructure. Privacy, GDPR. The cost of investment. And all the perception of unknown risks that are out there. Well, let's talk about one in particular, interoperability. As you can see, it's a little bit small for you. There are many different protocols and standards that tries to leverage different distance, different power requirements and latency requirements. LPWA, WA as an example, and many derivatives. It is a problem. And one of the biggest challenges that we see is interoperability, just getting things to work properly so you don't have to have multiple gateways. What are some other challenges? Well, if you take a look, we can actually start to break down the issues within security, such as encryption, as well as even coming in with the IP addresses, because 50 billion devices, I mean, that's a lot of different IP addresses. Matter of fact, when I spoke at the European Commission, they were just trying to come up with a framework to deal with the scaling issue, as well as the complexity and the optimization problems with all the new sets of metadata and the storage that's IoT brings. Well, before we can address how quantum computing might be able to help with some of these IoT obstacles and challenges, we first need to get acquainted with some of the fundamentals of quantum physics and quantum computing. Well, quantum mechanics, as some of you may know, is a branch within physics, and its fundamental theory is about the nature of small-scale things, such as low energy of atoms and subatomic particles. Classical physics, the physics that existed before quantum physics, derives the quantum mechanics as an approximation valid only at large, or what we call macroscopic with scales. Quantum mechanics, on the other hand, differ from the classical physics in that the energy, the momentum, the characteristics of both the particles as well as the wave, what we call wave-particle duality, and there are many limits to the precision in which quantities can be known, which is called uncertainty principles. By the way, for those of you that are linguists, the word quantum is derived from Latin, which means how great, how much. Because in quantum mechanics, it refers to a discrete set of units assigned to certain physical quantities, such as the energy of an atom at rest. The discovery that particles are a discrete package of energy with wave-like properties, it underlies the mathematical framework of many fields within physics and chemistry, including the condensed matter physics, solid-state physics, atomic physics, and molecular physics, and so forth. Let's talk about atomic orbitals. Quantum mechanics was initially developed to provide a better explanation and description of the atom, especially when it came to the difference in terms of the spectra of light emitted by the different isotopes of the same chemical element, as well as the subatomic particles. Well, one of the things that quantum mechanics incorporates are 4 separate classes of phenomena in which classical physics just simply cannot account for, such as quantization of certain physical properties, quantum entanglement, principle of uncertainty, and wave-particle duality. Quantum superposition. Superposition is essentially the ability of a quantum system to be in multiple states at the same time. It kind of sounds like my wife. Something that you can be here and there, up and down, all at the same time. Superposition frees us from the binary constraints of classical, which is based on bits, such as 0 and 1, right? Whereas quantum qubits provides values in 0 or 1, or both, simultaneously. And if you build 2 qubits, they can hold up to 4 values at once, which is very different, such as 0, 0, 0, 1, 1, 0, 1, 1. So you can see that there's a notion of factorization built in. Another important concept is around entanglements. It's a physical phenomenon that occurs when a pair of or groups of particles are generated or interact in ways that the quantum state of each particle cannot be described independently. It can't be separated, frankly. And when the particles are separated at large distances, I'm talking about ends of universe, instead a quantum state must be described for a system as a whole. And I'll talk about how it can be separated at far distances, but yet almost instantaneously, a little bit less than light speed, can communicate. Entanglements. It's because they become very entangled in their interactions. An entanglement is oftentimes broken when that entangled particle decohere through that interaction with the environment. For example, when a measurement is made. And that's part of the reason why they're having trouble currently in terms of development. Now, recent experiments have measured entangled particles with less than 1/100% of travel time of light. That's incredible. In other words, whatever the effects of measurement that happens is almost instantaneous. Now, equally interesting is that if you were to separate the 2 entangled particles, when we measure the characteristics of these particles, we find that the result of the first and the second particles will match, but of course in opposite values. Quantum teleportation and superdense coding. Now, among the best-known applications of entanglement is quantum teleportation and superdense coding. quantum teleportation is a process in which the quantum information, such as the exact state of an atom or photon, let's say, can be transmitted from one location to another location with the help of a classical communication channel. And shared quantum entanglement between the sending and the receiving location. Now, because it does depend on classical communication, which can proceed no faster than the speed of light, it cannot be used for faster than speed of light transport or communication of classical bits. Now, while it has been proven that it's possible to transport or teleport one or more qubits of information between two tangled atoms, it has not yet been achieved between molecules of anything larger than that. And it's important to note that quantum information cannot be copied nor destroyed. Quantum teleportation. I mentioned this at a presentation I gave earlier this week. And she said, that would be awesome. Well, actually, I'm not talking about you physically teleporting. Rather, it's a mechanism for moving the qubit from one location to another location without actually physically transporting the underlying particle that qubit is attached to. Well, much like the invention of telegraph that allowed classical bits to be transported at high speed across continents, quantum teleportation holds the promise that one day qubits could be moved likewise just through open space. Now, just to give you a little bit explanation, a little bit more here, it's a common illustration that they use. If Alice on the far left has a particle which is entangled with a particle owned by Bob, and Bob teleports it to Carol, well then afterwards, Alice's particle is entangled with Carol's. Very interesting. In other words, the state of Bob's first particle can be teleported to Carol's, although Alice and Carol never actually interacted directly with each other. Now their particles are entangled. Quantum cryptography. Now this, because of the shared noise of entanglement, makes for an excellent one-time pattern. And moreover, since measurement of either the member of an entangled pair destroys the entanglement that they share, entanglement-based quantum cryptography allows sender and receiver to more easily detect the presence of an interceptor. And this is very important for security purposes, which I'll describe later. The best known examples of quantum cryptography is the quantum key distribution, which differs from the information theoretically secure solution to the key exchange problem. Now the QKD, quantum key distribution that you're seeing, is the process by using quantum communication to establish a shared key between two particles without a third particle learning anything about that key, even if someone can eavesdrop on that communication between the two parties. Now, if someone does, in fact, learn information about the key, the interesting thing is that establishment is actually going to fail between the two parties to notice. In other words, just the mere fact that third party actually even looked at it will actually change the results. And once the key is established, it's then typically used for encrypted communication using classical techniques. Now let's talk about some of the more common encryption methods that you're probably familiar with, such as RSA. Well, this approach can be easily broken by quantum adversaries using Shor's algorithm for factoring and computing discrete logarithms on a quantum computer. Now the advantage of quantum cryptography lies in the fact that it allows completion of various cryptographic tasks that are proven or conjectured to be impossible using just classical communication. And it's impossible to copy data encoded in a quantum state. And the very act of reading data encoded in a quantum state changes that state. Fascinating. Bits versus qubit. Quantum computing studies the theoretical computation system that makes for that direct quantum mechanical phenomenon, such as superposition and entanglement that I just referred to perform the operation of data. Well, the quantum computers are different because of the fact that classical computers, like I said, have a binary approach when it comes to transistors, right? But when it comes to quantum computation, it uses quantum bits, which can be in superpositions of states. And a quantum Turing machine is a theoretical model of such a computer. And it's also known as a universal quantum computer. So let's get into the quantum computer side. Now, up to this point, large-scale quantum computers have been fairly theoretical in terms of how they could potentially solve problems much faster than the classical computers, right? Best known for algorithms such as integer factorization using Shor's algorithm, or the simulation of quantum many-body systems. Well, there are other algorithms, such as the Simon algorithm, that run faster than any possible probabilistic classical algorithm. In a classical computer, it could in principle simulate a quantum algorithm, of course, but a quantum computation does not violate the Church-Turing thesis. Whereas on the other hand, quantum computers may be able to efficiently solve problems which are not practically feasible on classical computers. Now, the biggest problem with quantum computing is Achilles' heel, which is a quantum decoherence. The field of quantum error correction examines how to stave off this decoherence and combat other errors. Now, this usually means isolating the system from its environment, as the interaction with the external world causes the system to decohere. And that's part of the reason why the current systems are so massive. Well, let's talk about the degree of decoherence. Things like quantum gates and the lattice vibration and background thermonuclear spin of the physical system used to implement qubits, all of these things cause noise. Now, the problem with decoherence is that it's not irreversible. I'm sorry, it is irreversible. It's a non-unitary, and it's usually something that should be highly controlled, but difficult. But we're starting to make some progress. All right, so let's go back to IoT. Why am I talking to you about quantum mechanics and quantum computing? What are the benefits for IoT? Well, before I get into the details, let me set some clear expectations. Quantum computing is not a silver bullet for solving every problem. That's not what I'm saying. Rather, when I'm presenting some of these possible areas of benefits used to implement qubits, it's really about the possibilities that we can see, because we're at a dialogue impasse where it feels like we can't get through some of the security, privacy, and interoperability and so forth. Well, in just a few years, we'll start to see some incredible breakthrough. It's really meant to serve as a rally to the industry to explore and to dig deeper. Like anything, you won't know the extent of the benefit until you can test it out against relevant use cases. Cybersecurity. Integer factorization. Now, this underpins the security of public key cryptographic systems. And it's believed to be computationally infeasible with an ordinary computer to do large integers. And that's exactly why we need quantum computers. Now, the classical systems cannot handle the factorizations that you're seeing here. We're talking about the product of prime numbers. Can you imagine finding the products of 2 300-digit primes? Well, quantum computing can do that very easily. By comparison, a quantum computer can easily and efficiently solve problems using Shor's algorithm to find its factors, unlike the classical counterpart. Now, this ability would allow for a quantum computer to decrypt many, if not all, the cryptographic systems that are used today. All of them can be cracked. In the sense that they will be polynomial time algorithm for solving the problem. Now, in particular, one of the most popular public key ciphers are based on the difficulty of factoring integers, or the discrete log problem, both of which can be solved by Shor's algorithm. In particular, like I mentioned, RSA, Diffie-Hellman, and elliptical curve Diffie-Hellman algorithms can be easily broken. Let's talk about computation. The quantum computer can harness quantum states to represent bits simultaneously, not serial, but simultaneously, and can do it exponential growth, meaning growth in speed and power. And the benefit is that institutions can solve huge, enormous, complex problems in a very short, reasonable amount of time. Now, this is relevant for IoT data because, as we know, we're talking petabytes, tetrabytes, zettabytes, and then you add the complexity of solving for an optimization problem. Well, because on the quantum level, we're able to program the atoms to represent all possible input combinations, all at the same time, simultaneously, and send it out. That means you can run an algorithm, all possible input combinations, and test it out all at once. That is incredible. Whereas with a regular computer, you have to serially cycle through every possible input combination to arrive at a solution. Meaning it's going to take a whole age, literally the age of the universe, to complete the most complicated calculations. For some problems, quantum computers offer a polynomial speedup. And the most well-known example of this is the quantum database search. I talked to you earlier about interoperability. Well, today's IoT standards are really constrained to the radio frequency wavelength capabilities of today. Whereas with quantum computing, we're not going to be restricted to data rates, range, and the fragmentation of the standards that plague us today. Now, just to be clear, it doesn't mean that there are not going to be protocols in the future, but we're not going to be constrained by the issues that we're having today. That also means that there will be no latency, network latency, because again, though we can't reach speed of light, we can get pretty close. And one of the really interesting things about quantum computing is that we're not limited by distance. Because it doesn't depend on classical communication. While it does depend on classical communication, it can actually reach almost the speed of light. And what that means is that when messaging or communication gets transferred, it can literally happen instantaneously over any distance without even the traditional talking infrastructure. Should quantum computers become miniaturized in the future, the sheer power of that quantum computing is going to be available on the edge devices, which is going to afford us to be able to run complex and massive data crunching, AI and machine learning and deep learning systems right on the edge. Moreover, increased storage capacity on the hard drive, which I'm going to talk about in a bit. Now, for those of you that are thinking, well, this is all theoretical, let me tell you a little bit about some of the recent developments. This is not 20 years away, this is 10 years away or less. Researchers have recently published a blueprint, like I said, for microwave trapped ion quantum computing. And the prototype is expected to be available in about 2 years or so. China has launched a satellite, it's the world's first quantum communication satellite, dedicated to testing the fundamentals of quantum communications in space. Now, this $100 million project was launched late last year. And they're going to be testing this for the next couple of years to check the feasibility of quantum communication between Earth and space. Again, completely bypassing telco infrastructure. Discovery of new phase matter. 2 different teams of scientists reported the discovery in the journal of Nature recently, and they're able to actually observe and create something called time crystals. Now, these are long theorized quantum systems that spin at their own pace independent of the environment. And it's just incredible because it seems to break the rules of normal timekeeping. Researchers believe that the underlying physics and technology used to probe such quantum systems could be very useful for quantum computing, especially when it comes to measuring sensitive quantum sensors. Researchers at the Swiss Federal Institute of Technology has published that they can actually store data in a single atom magnet. Amazing. That means that the rewritable device made from two such magnets is able to store just 2 bits of data, but the scaled up system could increase hard drive storage density by 1,000 times. Now, unfortunately, I can't go into all the detail because I'm being frank for time here, but in sum, the potential of quantum computer is incredible, from supercharging computation and certain types of computation to providing instantaneous data and communication exchange over any distance, whether you're at one end of the universe to the other, without the need for traditional infrastructure, including calculus. One of the hardest cryptography to break, as well as being able to break any classical approach today, and enable IoT on the edge that's rigorous and powerful. So, again, I realize that many of you are skeptics, but I encourage you to explore the possibilities of what quantum computer can do specifically within the Internet of Things. So with that, thank you very much.